and car. But just knowing that we're in a virtual environment, please be mindful of others and offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. And throughout the meeting, you always have an option to raise your hand if you'd like to make a comment. And we have 3 co-chairs, so we'll also be monitoring the chat, and we'll use that for any additional questions that go beyond what can be inserted during the Q&A after the presentations. So here's the agenda for today. We'll start with science presentations, 15 minutes talks, and ideally 5 minutes Q&A. Then we're going to break for a CGD seminar on molecular perspectives on Pliocene hydroclimate in southwestern North America. And Elizabeth, if you wouldn't mind putting that link in the chat so people can just click on that on the YouTube link, that would be great. And then we'll have a lunch break, and we'll come back again for presentations at 12:30, followed by a co-chairs update and a discussion. So some of the items we have for discussion is how the university community can collaborate with us a little bit more closely. What are your needs? What should we be doing with computing in year 2 if we have any spare time? So if there's anything else that comes to your mind and you would like us to address, then please put it in the chat this morning. We'll have a few minutes for the coaches to regroup. If there is something major we can add to discussion, we'll be happy to do it. And we're aiming to wrap around right around 2 p.m. Okay, so I think we're going to get started in with our first presentation. And the first presentation is from Hayami Kim, who is at University of Stony Brook, and I'll let her take it from here.
Okay, can you see the screen? Yes. Okay, thank you. Thanks for giving me the opportunity to present my recent work. This work has been in collaboration with James Benedict. And on the left-hand side, just to make sure we are all on the same page, the left-hand side shows the MGO life cycle. It's the precipitation anomaly composite by 8 phases of the MGO. So here you see the MGO is a unique type of tropical organized convection, and it has a planetary scale, and it varies intra-seasonally. So it has a 30 to 60 day time period. And it usually propagates from the Indian Ocean to Western Pacific before it dies where it meets the cold SST. And as the MGO propagates, it impacts the global weather and climate system, as you see on the right-hand side. And that is why the MGO is regarded as the major source of subseasonal predictability. So it is very important to predict this phenomena, the MGO. And as you can see from here, this is the if you see the propagation, the anomalies, and you see this, it starts in the Indian Ocean, which is in the Indian Ocean, and then propagates through the maritime continent in the observation, and then Western Pacific. And we can separate this MGO phases into 8 phases using the William-Hendon RMM index. So RMM is real-time multivariate MGO index. And in the earlier phases, when MGO is in Indian Ocean, you see that these phases are earlier phases from 1 to 3. And then as it propagates through the maritime continent, it changes from 5 to 6. And then later phases are where when the MGO enters the Western Pacific. So it's important to predict this phenomena, especially this nice propagating phenomena. However, in our the climate system, in the weather forecast models, this phenomena, when the MGO starts in Indian Ocean, most of them decays before it enters the maritime continent. So that has been a big issue in the last decade. So today I'm going to introduce the maritime continent barrier effect on MGO predictability. So if we have how much of this maritime continent can impact the MGO predictability. And we use the perfect model ensemble forecast with the CESM Aquaplanet. So just to give you a brief introduction of where we stand in terms of the MGO prediction. So this is the MGO prediction skill. It is the RMM index anomaly correlation coefficient. So y-axis is correlation and x-axis focus lead time. So here RMM index is again a real-time multivariate MGO index, such as similar to a linear index or Nino 3.4 index. So these are the two time series of which represents the MGO, and we can compare the forecast of this RMM index with the observed RMM index. So, and then we can calculate the anomaly correlation coefficient, and this shows the prediction skill in S2S and sub-X models. So the dashed line is the S2S models and sub-X models are the solid lines. So what you see here is that if you have the 0.5 line as a threshold, you can see the ECMWF model has the best skill. It is about 32 to 33 days. And then, but the next group, the best group is these models, which reaches about 25 to 27 days of correlation coefficient 0.5. And the CSM1 and CSM2 are all in this good MGO prediction group. So, and you can see that most of the models, the majority of models ranges are between like 3 to 4 weeks of a prediction scale. This is the anomaly correlation when we consider all the MGO events, all the MGO forecasts starting in any phases, but then we can also separate it into 8 phases and see how the amplitude of the MGO changes. So this is the MGO amplitude bias, and it's a little bit complicated, but so let me focus on the CSM1 first. So y-axis is the initial MGO phase. As I mentioned before, MGO can be separated into 8 phases, and when at the time of the forecast, the MGO can locate in any location. So when you separate it into 8 phases, this shows the amplitude bias. So the brown shading, x-axis is the focus lead time. So the brown shading means that when the MGO starts in all your phases, like 1 to 3, where the MGO is in the Indian Ocean, then it loses its amplitude faster. So this is the bias, and that is the model minus observation. And then when it starts in the later phases, it gets stronger, but overall, after 2 weeks, it gets overall weaker. That is not just the problem of this model, but if you compare all the sub-X models, you see that in the earlier phases, you can see the brown shading, which means there's a weaker amplitude at phase 1 to phase 3. So that means there's a quick decay of MGO signal when the MGO starts in the Indian Ocean and propagates through the maritime continent. Also, the ECMWF model, which is the world best model, you can see still this decay of the MGO signal when it starts earlier. In the later phases, there is no big bias in this, no amplitude bias, but it's only in the earlier phases. So this is the sub-X models, which indicates the maritime continent prediction barrier. And another example is the S2S models. So here, this is from Bitard. This is the S2S models, and here the y-axis is the percentage of MGO events starting from Indian Ocean and not crossing the maritime continent. So in the ERA interim, only in the reanalysis, only 10% of the MGO starting from Indian Ocean do not propagate the maritime continent, but in the models, in the S2S models, they are almost double. So that means there is a maritime continent prediction barrier. So here, just to show you how it looks like. This is the MGO propagation. So x-axis is a longitude and y-axis is focus lead time. And here is the NOAA ORR, and the shading is the ORR anomaly, and the contour is the U850 wind. And you can see that in observation, when it starts over the Indian Ocean, it propagates. And here 120 east line is the center of the maritime continent. So you see the nice propagation. However, in the, for example, in the ECMWF model, the signal decays before it propagates through the maritime continent. So our question is then, we know that in the models, in all S2S and sub-X models, the models struggle with this maritime continent prediction barrier, but how much of prediction skill is reduced by this exaggerated maritime continent barrier is not quantified yet. So in other words, how far can the MGO prediction skill be extended by overcoming the exaggerated MEMC barrier effect? So that is what we want to address. So to address this, we decided to use the simplified models, so the reduced complexity models. And this is we use the CESM2 Aquaplanet. Here, this shows the mean state for 10 years. Let me introduce the Aquaplanet first. The CSM, we use the CSM2 Aquaplanet, and that here you see this configuration. It has this 0.9 times 125 resolution and 32 vertical levels, and the Earth is completely covered by water. So there's no topography, no sea ice, it's just covered by water. And we use the prescribed SST and the perpetual equinox insolation. So there's no seasonality, but there is a diurnal cycle. So the Aquaplanet, this is the Aquaplanet, and here what we prescribe is the wormhole SST. This is the zonal asymmetric SST. And the reason why we prescribe a wormhole is because not only the basic shape, but also MGO is it's reasonably simulated than the symmetric SST. So here are some details of how this wormhole SST is prescribed, but we'll skip that. And here this shows the SST, and right-hand side is the precipitation, the mean precipitation and the low-level wind field. So you see that the precipitation or convection occurs where the wormhole exists, and also the local Hadley circulation and Walker circulation is also reasonably simulated. One thing to what we changed here is the entrainment rate. So we increased the entrainment rate, and that is to make the convection more sensitive to tropospheric moisture. And that is because it is crucial for MGO simulation. So the models which has more sensitivity of convection to tropospheric moisture tend to simulate the MGO better. So we increase the entrainment rate. So in the CAM6 default version, it is 1 times per kilometer, but we increase this to 2 times, 5 times, and 10 times per kilometer. So increase the entrainment rate. So just to show you, before we move on to MGO, just to show you how this moisture precipitation coupling changes, here is the y-axis, x-axis the precipitable water, and y is the precipitation. And we here in the observation, this the red line, you see that the precipitation over the tropical ocean occurs, the convection occurs when the precipitable water or the moisture has a certain threshold, and then when it reaches a threshold and then increases exponentially. However, in the CAM6 default, here it is WP1, so that is the wormhole times 1 simulation. So that is the default version, and you can see that the convection starts too early in the low moisture regime, and that is also a problem in most of CMIP and S2S and sub-X models. So when we increase the entrainment rate, you can see that if we change it to 10 times larger, then at least in this side, on the right-hand side, it gets closer to the observed, and also MGO is better simulated. So here this shows the tropical modes of variability overall in the wormhole CAM6 default. This is NOAA, and this is the default version. And then on the right-hand side is when we increase the entrainment rate 10 times. And you see that overall the equatorial waves and MGO gets more stronger and also more closer to the, it gets more realistic. So, and this shows the MGO life cycle. The left-hand side is the NOAA and ERA interim, and right-hand side is the wormhole run. So here we can calculate the RMM index and then make the composite, and it shows the wormhole run. Although it's simplified and it has only the SST wormhole prescribed, it kind of simulates or captures this eastward propagating signal, as well as the wind structure with reasonably. So in conclusion, we will. So the wormhole run is now is the entrainment rate increased entrainment rate. And overall, this CSM2 Aquaplanet wormhole simulates reasonable mean state and MGO-like mode. So we use this as a default. And then what we want to do is how the maritime continent impacts the MGO predictability. So again, here, this is the top panel is the wormhole run SST and precipitation that I showed before. And then what we did is the maritime continent barrier run. So we wanted to have the MGO not propagating through the maritime continent. So we use this surface. First of all, here you can see the SST is colder than the wormhole run, and here only over the maritime continent. So here the surface topography mimicking the maritime continent land masses is set to Earth-like values and remain zero elsewhere. And then the SST over this maritime continent decreases with elevation using the 6.5 K per kilometer lapse rate over this maritime continent. So it's a cold aqua mountain. Then if you compare the difference between the SST difference between MC barrier minus wormhole, you see that over the maritime continent, it's much colder. So, and precipitation, if you compare the precipitation you see here over the maritime continent, the convective activity is suppressed and it's much drier. So we have colder and drier maritime continent. And here this shows the precipitation activity, so convective activity. So here on the left-hand side, it's the wormhole and the arbitrary 500 days. And you can see this, the convective activity is active over the wormhole area, but then when the maritime continent barrier or the aqua mountain is prescribed, then you see there's the convective activity is suppressed. And also we can compare the MGO activity, which is defined as the standard deviation of 20 to 100 day filter precipitation. And in wormhole simulation, there is no overall everywhere is active, but then in the MC barrier run, you can see this kind of two maxima here, and then over the maritime continent, it is suppressed. So as we expected, in the MC barrier run, there is an overall weaker convection and MGO activity over the maritime continent. Now what we want to look at is the MGO propagation. So this shows the lag correlation of the shading is the filtered ORR and the contour is zonal wind at 850. And tropically averaged, and the reference point is over the Indian Ocean. So x is longitude, y is lead and lag, and the values are the correlation. So in the wormhole simulation, as we expected, the wormhole simulation can have this eastward propagation of the MGO-like mode, but in the MC barrier run, you see that in this this line is where the maritime continent starts, and you can see that it does not propagate. So now we have successfully simulated the propagating and this MC barrier run. And this this pattern mimics the current S2S and sub-X MC barrier issues. So back to our original question is how much focus scale is reduced by the maritime continent barrier. So we did a perfect model focus experiment, and the left-hand side is there are two steps. So one is the perpetual run, which is here we have the 10 years or 120 months of the run. And here we use the wormhole SST, so the wormhole SST prescribed, and then keep the restart file every 10 days. And then the right-hand side is the perfect model forecast, we use this restart file and then perturb the initial conditions, the temperature field, and then make 10 ensembles, and then you have the 45-day forecast. And then we compare this 45-day forecast with the truth. And if we do this, if you do the 45-day forecast with the wormhole SST, that gives us the MGO predictability, because we are comparing the same model, and that means that we assume it's perfect model, and there is no error from the model, but only from the initial condition. And then the second run is the MC barrier run. So for the 45-day forecast, we prescribe the maritime continent barrier SST. So with the one pool SST, we can calculate, we can estimate MGO predictability. And then with the MC barrier run, we can estimate how much predictability is lost by the maritime continent barrier. So this is my last slide. We compare the RMM index, the same method that we used in the forecast models. And here the here the blue line is the one pool simulation. So it's approximately, if you keep the 0.5 line, it is about 42 days. So that means the upper limit of MGO prediction. If the if the model is perfect, then we'll have 6 weeks of predictability. And then the MC barrier run is when we compare the models which has the maritime content barrier, so MGO not propagating, there's about 10 days loss of skill. So yeah, so we found that this is the conclusion. So we found that the intrinsic MGO predictability is approximately 6 weeks, and then the skill reduces to about 4.5 weeks, so 10 days less when the MGO is impeded by the maritime continent barrier. I think I have to stop. Thank you very much.
Thank you very much, Hayami. That was super interesting. Does anybody have any questions? If you could raise your hand. Okay, there's a question in the chat from Andrea. The barrier effect seems to be a lot weaker, maybe too much so at very high resolution, 6 kilometers atmosphere, 4 kilometer ocean, for example. Any thoughts about why this may be the case? Just a matter of resolved atmospheric convection?
Also, in high resolution models, the barrier effect is weaker, so that means the MGO propagates better. I think that's the point. Yeah, I don't have a clear answer for this high resolution models. And so most of the models that I saw is they have the exaggerated barrier effect. So I don't have a clear answer. Sorry about that.
No problem. Next question from Jerry.
Yeah, that was really interesting, but I was just curious. It looks like the barrier effect has to do with the topography of these big islands in the maritime continent, but in the real world, there's big island topography in the maritime continent. So is it something with the boundary layer formulation in the model that it can't go over these islands well, or what? I mean, what's actually the ultimate solution to this problem when you're using real world topography and things like that?
So I think in the S2S and sub-X models, they have the very strong dry bias in that area. I don't have it here, but overall strong. Yeah, dry bias in this area in the most models, and that can impact the MGO propagation because of for the MGO to propagate, it needs a moisture advection. So the advection of the moisture by MGO, so the mean moisture by the MGO based on the moisture mode theory. But that is because in the models they have almost dry Indo-Pacific area, so it does not advect enough moisture for the MGO to propagate. So that is one answer.
Yeah, so I guess then the follow-up question would be, well, how do you fix that in the model? Do you do something to the land surface processes over the big islands, or how do you fix that?
Oh, how to fix that? Yeah, I think it's still not very clear to how to fix that. My answer is that in the S2S model, we also find this dry biases overall, and that is related with the convective parameterization. So in all the S2S models, they start to have convection when the moisture is not enough, when the environmental moisture is dry. So that can be one solution. But how this the land effect impacts directly to this is not. I don't have a clear answer for that.
Okay, thanks.
So The last question, hopefully not too long, from Rich.
Okay, try and make it quick. I mean, my first thought is, I don't know if you've looked at the climate, but that 10x on the entrainment is super high. And I wonder whether you have got any real grid scale, any parameterized convection at all so high. Also, just to follow on from Jerry's point, yeah, it's interesting. I wonder if you've looked at the Diurnal cycle, because often the problem with the barrier effect is not a physical or a surface flux effect. It is often excessive Diurnal cycle, very persistent Diurnal cycle precipitation, which kind of interrupts the MGO.
Yeah, that's right. So to answer your first question, the diurnal cycle in this simulation is suppressed because we use the prescribed SST. So there's almost like the surface flux and the surface flux. And yeah, so it's almost no diurnal cycle, very weak diurnal cycle. So it does not impact the results here. The first question is about the simulation here, the worm pool. But we found that with 10 times entrainment rate, the mean state is also closer to the real world. I mean, it's closer because in the default version, it shows kind of double ITCZ, but then it changes to the single ITCZ and matches better with like this one is actually using the 10 times entrainment rate, which matches better with the worm pool or the prescribed SST. And also MGO gets stronger and propagation is also better simulated.
All right, thank you so much, Jaime. If you have additional questions, put them in the chat and we'll move on to a talk by Kai Huang. Kai is a graduate student at GMU, and as you imagine with COVID, he's not had a lot of chance to travel to meetings. So if you have additional comments for him, feel free to use the chat or reach out to him offline. Go ahead, Kai.
All right, can you see my screen? Okay.
Yep.
Okay.
And now we see two of, there you go, perfect.
Okay, cool. So my topic today is about the MGO QPO connections in MGO case handcuffs using CESM prediction system. And this work was done in collaboration with Dr. Ricker and Inkar and my advisor, Casey Pigeon. So the observation shows the QPO had a strong control of the MGO, that MGO is more likely to propagate across the maritime continent during the QPO easterly years than during the QPO westerly years. And such kind of differences is only robust in the winter season and is validated by various diagnostics using the RMM index, Rho-me index, and also all kinds of Hofmuller diagrams. But still, the understanding of such connection is very limited. There are several proposed mechanisms for it, but without validation. And this is probably due to the fact that the observed MGO QPO connection cannot be captured by current GCMs. There are actually several tries to reproduce the MGO QPO connection in the models. There are successes and there are also failures. So the first two successes are focusing on the case handcuffs in the regional model. Both successes are using the Wolf regional model, and they focus on the MGO case handcuffs, and they attribute to these successes to the triple Bose instability theory. But using the regional model has one potential problem, that the constraints are somewhat strong compared with the GCMs, that only the local responses can be considered in these regional models. While some theory like the wave reflection theory really needs some non-local responses and is probably not very well investigated in these regional models. And there's a big hope in the prediction system. There's a success in the ECMWF system, and they found to successfully reproduce the stronger MGO convection signal in the QPO easterly years than in the QPO westerly years. And they conclude that the stronger predicted convection in the QPO easterly years is dominated by the initial troposphere. But that leads to another potential question, is that whether the MGO is already stronger in the initial conditions from the QPO easterly years than in the QPO westerly years, that such kind of success mainly comes from the memories from the initial conditions rather than it is the model is doing something right. And it is interesting that when they use the GCM climatology simulation try to reproduce the MGO QPO connection, they encountered a failure using this GCM. And that really leads to another potential question is that whether the MGO structure is somewhat biased in this GCM. So to answer these potential questions, we designed our own experiment using the CESM prediction system. This is due to the fact that there's a hope in the prediction system, and also we use the CESM prediction system is a GCM rather than a regional model, so the non-local responses can also be investigated in this prediction system. And also, in order to rule out the QPO's influences on the MGO in the initial conditions, we will select strong MGO cases in the QPO neutral years. So we would like to call them as clean MGO cases, that the MGO structure in these initial conditions are free from the influences of the QPO. And then we will introduce the QPO signals into the sensitivity rounds for our sensitivity experiments. We will nudge the QPO easterly and westerly temperature and U anomalies into these rounds respectively. And this nudging are done in the Zuda mean, as the QPO is mainly a Zuda mean mode. And these are the three cases we select for our studies. These are all very strong MGO cases, and they successfully propagated across the maritime continent. And these are the different sets of experiments we will run for each of the MGO case. So there were 6 sets of experiments in total. So the pre-control experiment is a totally free run without any kind of nudging. The purpose of the pre-control run is to provide the reference state for nudging for this sensitivity experiment. So for each sensitivity experiment, it consists of 3 rounds: the control round, the QPO round, and the super QPO round. So in the control round, the desired variable is nudged in the Zuda mean to the exact state as in the pre-control round. And this can be used for a reference. And for the QPO round, the same variable is nudged by also in the Zuda mean, but before the nudging, we will add the QPO signal into the nudging files. So in the QPO round, the QPO is introduced. And for the super QPO round, before we adding the QPO signal into it, we doubled it to mimic a super QPO scenario. So these are all 5 sensitivity experiments we would like to run here, and with different variables to be nudged in slightly different ways as shown by this table. So these are the QPO signals we added to our QPO run and super QPO run. These are calculated by doing the composites for the temperature and the U in QPO easterly years and QPO westerly year DGF season respectively. And these are some details of the nudging. I will just skip it. So for the first case, we have completed all the 6 sets of experiments, including 1 pre-control run and 5 sensitivity experiments. And we found that only in the QPO-T free U experiment, where only the QPO temperature is added and nudged into this sensitivity experiment, the MGO shows a correct response to the imposed QPO signal. So these are the time evolution for the equatorial profiles, vertical profiles for the temperature, as represented by the shadings here, and also the lunar wind as represented by the lines here. So the differences between the control run with nudging and pre-control run, which is a totally free run, shows that nudging actually did a very pretty job here, that these differences are very small. And also these differences between the QPO easterly run, QPO westerly runs, and the control run show that we successfully introduced the QPO temperature into these runs, and same for the super QPO runs. And it is also very interesting to note that although we did not nudge the QPO wind anomaly into this run, some free evolving QPO wind anomalies are evident, although they are not nudged. And this is both true for the QPO experiment and super QPO experiment. And we found that for this predicted MGO case, the both ORR and U200 shows correct response to the introduced QPO signals. On the left here are the Hofmüller diagrams for the ORR anomalies. And we found that in the QPO experiment, there are amplification of the ORR signal over the central western Pacific, which helps the predicted MGO to propagate further into the Pacific in the QPO east year than the QPO west year. And after we doubling the introduced QPO temperature anomaly, this kind of contrast is more obvious as shown by these 2 Hofmüllers here. And the amplification of the negative ORR signals over the central western Pacific is also more obvious. For the U200, we also see the correct response here, as in the QBO-West runs, the predicted U200 is more like a stalling mode rather than the eastward propagation mode over the maritime continent. While for the QBO-East runs, now the U200 shows a very robust eastward propagation. And this is more true for the super QBO experiment. For the super QBO-West runs, it is very much stalling over the maritime continent. However, for the super QBO-East run, the eastward propagation is very robust here. And we also calculated the RMM index amplitude and ROMI index amplitude to quantify such kind of differences. So each circle in this plot actually represents individual ensemble members, while the ensemble mean are represented by the solid dots. And also days with the differences between super QBO easterly and super QBO westerly runs passing the 19% confidence level are marked by these stars. So we can see a very robust differences of the RMM amplitude between the super QBO easterly runs, which is very strong, and the super QBO westerly runs, which are very weak. So these kind of differences pass the significant level test around day 21 and around day 35. That is when the MGO signal is over the maritime continent and over the Western Pacific. And similar situation for the ROMI index. Here, the differences are also very strong and could pass the significant level test. And this is very in agree with the observation that the QBO's influences on the MGO propagation and amplitude is the strongest when the MGO convection is over the maritime continent. So to get a better sense of how the ORR signal or the convection related to the MGO is changing in different sets of runs, we projected the ORR anomaly field onto the first two leading EOFs of the ROMI index to get the signals only related to the MGO. And again, here we can find that in the QBO experiment, the amplification of both the active and the suppressed phase of the MGO convection is evident after day 30. And such kind of amplification is mainly over the maritime continent and Western Pacific. And after doubling the input QBO signals, this kind of contrast is even more stronger and starts with an early date. And for the second case, we only completed the QBO-T3U experiment, but again, the MGO shows the correct responses to the imposed QBO signal. And similar things here. So again, the nudging did a pretty good job. The differences are very small, and we successfully introduced the QBO signals into the temperature signals into these rounds. And again, free evolving QBO wind anomalies are evident, although they are not nudged. So these are the predicted ORR and the U200 like Hofmüller diagrams. So in the QBO experiments, we show some kind of amplification of the ORR signals over the Western Pacific, but it is very weak, much weaker than we see in the first case. But after we doubled the input QBO anomalies, this kind of contrast between the super QBO easterly and the super QBO westerly phases is very robust. Now, during the super QBO westerly predictions, the predicted ORR system can propagate further into the Pacific, reaching to the dateline. And such kind of amplification is very obvious if you look at these differences between the Hofmüller diagrams. But it is interesting that if we look at the U200 for the second case, the U200 does not change much. Both in the QBO experiments and super QBO experiments, we see very little much change for the eastward propagating of the U200. And again, this kind of differences is quantified by using the RMM amplitude and ROMI amplitude. There are several days that could pass the where these large differences between the super QBO easterly and super QBO westerly runs could pass 19th confidence level test. And also for the ROMI amplitude, there are several days that could pass confidence level test. But again, compared with the first case, the second case responses is somewhat weaker. And these are the ROMI ORR Hofmüller diagram for the second case. We still can see the implication of the active MGO convection phase and the suppressed MGO convection phase around day 20. But again, compared with the first case, the responses is somewhat weaker, but the structure or the pattern is still here. And in the supercubial experiment, it becomes somewhat stronger, but still weaker than the responses in the first case. And there might be some possible reasons for the weaker responses for the second case. And one of which I really would like to talk about it because it will be very interesting. So the observation shows the cubial's influences is the strongest over the Maritime continent and the Western Pacific. So it is worth investigating why the cubial influences on MGO has such kind of a location preference. It is possible that my cubial needs some time to modify the MGO structure over the Indian Ocean. And when several days later, when the MGO convection is over the Maritime continent, it's very much different in the cubial east phase and cubial west phase. So these kind of differences leads to the different propagating features of the MGO over the Maritime continent. And if that is true, note here that our first MGO handcast is initiated when MGO is over the Indian Ocean, and the second MGO case is initiated when the MGO is already over the Maritime continent. It is possible that cubial may not have enough time or time long enough to alter the MGO structure much before it reaches to the Maritime continent or the Western Pacific for the second case. So we will try to investigate this, whether this will be true in our future work. And finally, some summary and outlooks. We conducted some handcasts of 3 MGO cases in the cubial neutral winters using the CESM prediction system, and their temperatures are notched and cubial signals are notched into these experiments. And we found only the MGO in the cubial T3U experiment shows correct responses to the introduced cubial signal. And we will investigate in our future that first, which part the cubial signal is responsible, whether it is the notched cubial temperature or it is due to the freely evolving U anomalies. And also we will do some research on the detailed physics responsible for it and try to investigate which of these 3 proposed possible mechanisms are more true or more responsible for such kind of responses. And that's the end of my presentation. Thank you.
Thank you very much, Kai. Are there any questions? So I'm not seeing any raised hands at this time. So I'll ask you a question. So did you listen to Hayami's talk beforehand?
Yeah.
So I was wondering if maybe trying some of the entrainment rate increases would also be useful experiments to perform, and if you had any thoughts on that.
Yeah, I think that will be interesting to do. Yeah, and since we are not sure which kind of mechanism is working here, maybe we can try to change the parameters or alter the physics in our models to do more sensitivity experiment. Yeah, that's a good suggestion.
Yeah, and Hayami had to go to teach class, so but yeah, that would be great maybe to follow up with her. And yeah, if we can learn from what she's done and put that into your simulations, I think that would be really useful.
Yeah, thank you.
Yeah. Anybody else? All right, if not, then we'll move on to the next talk, focus on subseasonal, and then we'll go into a longer time scale. So the next presentation will be by Hui Lee from NCAR.
Can you see my screen, Yaga?
Yep, perfect.
Awesome. Okay, hi everyone. My name is Hui Lee. I'm a project scientist at CGD NCAR. So today I'm going to present subseasonal tropical cyclone prediction in CESM2. I want to first thank Yaga Richter, Chai-Ing Lee, and Hayami Kim for their contributions to the work. Okay, so subseasonal tropical cyclone predictions are important because, first of all, tropical cyclones are extreme weather events that can cause major damages to coastal areas. So reliable TC predictions are important for guiding storm preparedness and protecting public safety. Subseasonal TC prediction has received a lot of interest in recent years, partly because of the improvement of the dynamical forecast models. And the aim of the research, most of the subseasonal TC prediction research is to explore the scale of probabilistic TC prediction beyond the current prediction time and identify windows of opportunity for increased forecast scale. So here today, we're going to investigate the TC subseasonal prediction in the CESM2 prediction system. This slide is provided by Yaga. So the CESM2 prediction system uses the CESM2 CAM6 model. It is the default NCAR CMIP6 version of the model. It has a 1 degree horizontal resolution in the atmosphere. It has a 40-kilometer top with 32 vertical levels. And the subseasonal prediction system follows known as the sub-X protocol. It initializes every week on Monday. Each round is 45 days long. The atmosphere and the land initial conditions are from the CFS2, and the ocean initial condition is from the GRE 55. There is a reforecast product from 1999 to 2020. It has 11 ensemble members. And there's also real-time forecast since April last year. It has 21 ensemble members. So the goal of today's talk is to evaluate subseasonal TC prediction in the CESM2 and also improve our understanding of the factors that can affect TC prediction scale. So in order to do that, we will first track all the TCs or TC-like storms really in these forecasts. We do this for the year of 2002 to 2019. We utilize all 11 ensemble members, and the TC tracking is applied on the 6-hourly output of the forecast. We use the Tempest Extreme Tracking algorithm based on closed contour criteria, also threshold criteria. And we had to adjust the detection threshold to account for the relatively coarse resolution. This is a 1 degree model. And then how do we evaluate the forecast scale? We focus on the basin-wide TC occurrence, and it's evaluated at a weekly temporal resolution. So coming to the results, which we will present according to this order, we will first evaluate the predicted TC climatology, and then we will evaluate the forecast scale in terms of basin-wide TC occurrence on the weekly temporal resolution. And then we will try to understand the factors that can affect the forecast scale. And lastly, we will investigate connection with MGO. Moving on to the first part of the result, the TC climatology. So here on the left figure, we're looking at the TC genesis density during this time period. And the top left is from the observations. The top right is from the week 1 forecast. We can see that week 1 produces very similar TC spatial distribution to the observations. And the rest of these panels are showing the differences from the forecast at different lead time and the observations. So we can see again that at week 1, the differences are relatively small, but then we notice that at week 2 and longer, there's a big decrease of TC genesis across all the TC basins. And these errors seem to persist from week 2 to week 6. And a similar result is found for TC track density. Again, the bias for week 1 is relatively small, but then from a week 2 to week 6, there is a large decrease of TC track. And if we took a look at the annual mean TC number, which is shown on the left figure here. So here the x-axis is different TC basins, and it shows the annual mean TC number in the observations and the mustard yellow column. And then on the right is different forecasts at different lead times. So first of all, we see that if we look at the global total TC number, the week 1 forecast had underestimate TC number, but it's within a reasonable range. But then at week 2, the simulated TC number drops by half, and which is a big drastic decrease. And then from week 2 to week 6, there is a slight increase of TC number with lead time, which we will try to explain in the next few slides. And then on the right, we're looking at the seasonality of the forecasted TC, the black line is observations. So we can see that, first of all the forecasts from week 1 to week 6 are able to capture the TC seasonality in almost all the basins. And the decrease in TC number we saw in the annual total number mainly happens during the main TC season in each basin. So yeah, that was the predicted TC climatology. And next, we're going to move on to look at the forecast scale. So we evaluate the prediction scale using the Breyer scale score. The Breyer scale is defined as this. It's just basically a squared error of the probability forecast. So here the O is the observation at each forecast time, and P is the probability forecast at the time, which is defined as this, which is basically the ensemble mean of the predictions. And both the prediction, the capital P, and the O are 1 if there is TC occurrence at the forecast time, and they're 0 if there's non-TC. And then this Breyer scale from the prediction is then compared to this reference Breyer scale, which uses the observed long-term mean climatology as a forecast. And then together they form this Breyer scale score BSS. So we can see that if the model has a better scale than the reference climatology, then the BSS would have a positive value. And also we use 2 different definitions for the reference forecast. One uses the annual mean constant climatology, BSSC, and another one is a monthly variant climatology. We call it BSSM. That's all I want to say about BSS, right? Okay. Okay, the right panel shows the prediction scale measured by BSS. There's a lot of lines here, but let's figure it out together. So each panel shows the prediction scale in one of the TC basins, and then x-axis is the forecast time from week 1 to week 6. And we just focus on the red line here. The red line here shows the BSS score compared to the constant annual mean climatology. So one can see that, first of all, in all of these basins, the red curve are above 0. And that means that the model is more skillful than if you just predict the TC occurrence based on long-term mean annual constant climatology. And this is largely because the model's ability to capture the TC seasonality. And then the blue line in each panel shows the BSSM, which is the prediction scale compared to the monthly variant climatology. And now we can see that the prediction scale actually is not looking very good. It's only positive at week 1 in the North Indian Ocean and Southern Hemisphere, and marginally positive in the Northwestern Pacific and Eastern Pacific. And the rest of the forecast time, they're all negative. So this tells us that the model is not very skillful in terms of capturing the deviations from the TC annual cycle. Oh, no, you know what? And in comparison, we also plotted the prediction scale of the ECMWF model, which is shown in this gold line in each of the panel. So we see that the EC model is better in terms of prediction scale at week 1 in all of the basins. And also it can capture, it's also skillful at week 2 forecast time in North Atlantic and Northwestern Pacific. Also plotted is the purple line, which shows the results from the NSEP model. We see that the NSEP model compared to CSM2, sometimes CSM2 is better, sometimes NSEP is better compared, in terms of different basins and lead times, but their prediction scale is relatively comparable. So that was the prediction scale. It turns out the model is skillful in capturing TC seasonality, but not as skillful in capturing the deviations from the TC annual cycle. And then at the next step, we want to try to understand the factors that can affect the forecast scale. And we're going to focus on mean state bias and the effects of initialization and TCCs. Okay, the first is the mean state bias. We're going to evaluate the mean state using the Genesis Potential Index, GPI. It is defined as this. It's a function of low-level vorticity and mid-level relative humidity, TC potential intensity, which is a function of SST and atmosphere vertical profile, and also vertical wind shear. It kind of combines all the factors that can affect TC into one index. So here, the top 2 panels are showing the GPI in the reanalysis in their respective hemisphere TC seasons. And the rest of the panels are showing the differences between the model forecasts and the reanalyses. So first of all, we can see that at week 1, in the Northern Hemisphere, most of the basins are very similar to the observation, but then in Northwestern Pacific, there is an overestimation of the GPI, and the Southern Hemispheres, there's also an overestimation. And then as the forecast lead time goes on, we see that the GPI in the Northwestern Pacific, as well as the Eastern Pacific, increases with time. And the Southern Hemisphere there's always a positive bias. And also there is a negative bias in North Atlantic. So the main thing we find is that actually the model has increased or a positive bias of Genesis potential index, which means that the model's environmental conditions are more favorable to TC genesis at longer lead time, at least in these Northwestern Pacific, Eastern Pacific basins. And this is opposite to what we saw before in terms of the simulated TC genesis and prediction scale, because we saw at week 2, there is a drastic drop of TC number. So this tells us that the large scale environmental factors is conducive to TC activity, and that the environmental factors is not really the main cause for the TC, for the simulated TC number or prediction scale. So that leaves us with the next option, which is another very important factor that it can affect TC genesis, which is the TCCs, or the convective disturbances. And they mainly come from ITCZ breakdown or African easterly waves. So we detected the TC precursors in the model using a similar method in detecting TCs, but this time we'll only apply the closed contour criteria. So the week 1 forecast, we see that there's TCCs all over the main TC activity area. And then the rest of the panels are showing differences between different weeks and week 1. So as expected, actually, we see that from week 2 and longer, there's a drastic decrease of TCCs in the forecasts. So from here, we can see that the TCCs is actually the main reason why we see a big drop of TC number and the prediction scale at week 2. So we think the main reason for this drop is probably the model resolution. So a higher model resolution is needed if we want to capture, if we want to have a better subseasonal TC prediction. And lastly, we wanted to investigate the connections with modal variability. Because a subseasonal TC activity is found to be closely connected to the MGO, we're going to look at how the MGO TC relationship is presented in the model. This slide is also from Yaga. It shows the MGO scale in the CESM2. The CESM2 is the red line here, so we can see that the MGO is predictable out to 25 days in CESM2. And excuse me. This figure shows the TC track density anomalies in MGL phase. So basically, each of this, the top row shows the anomalous TC genesis activity during different MGL phases in the observations. So we can see that the TC activity in the observation actually propagates eastwards as the MGO phase moves on. And then we examine this relationship in the forecast. We only plotted week 1 to week 3 in here. So we can see that the eastward propagation of active TC genesis with MGO phase is also captured in the forecasts at up to 3 weeks of lead time. And after 3 weeks, the signal is not very distinguishable. So from here, we can see that the MGO is actually a very important source of predictability for subseasonal TC prediction. So a better improvement of simulation of MGO would help us to improve the TC subseasonal predictions. Very encouraging results. And this is my last slide, which summarizes the whole research. So basically, we examined the subseasonal TC prediction from 2002 to 2019 in the CESM2 subseasonal hindcasts. And we evaluated the predicted TC seasonality and found that the TC number quickly drops at week 2 and longer. And then we evaluate the forecast scale in terms of basin-wide weekly TC occurrence. And we find that the model is skillful at week 1, but quickly deteriorates for week 2 to 6. and if we compare to monthly variant observed climatology. And then next, we try to understand the factors and affect the forecast scale. We find that it is primarily the reduction of TC number at longer leads is primarily due to reduced TCCs rather than the mean state conditions. The mean state conditions is actually favorable for TC genesis. And lastly, we investigate connections with MGO. I actually didn't show ENSO here because I thought the time was limited. But anyways, the TC-MGO connection is well represented at week 1 to week 3 lead time in the model. And that's what I want to show today.
Thank you very much. Are there any questions? Don't be shy to raise your hand or put a question in the chat. Jerry, go ahead.
Yeah, that was really nice, Hui. So I was just curious about these TC seeds. Not being really familiar with the tropical cyclone research, I mean, are the TC seeds well understood as to what they are and how they function and how they interact with the background base state?
Yeah, actually, there's a lot of research on the TCCs. They're just the pre-existing disturbances that eventually develop into TCs. And most of the times they come from ITCZ breakdown and African easterly waves. And actually, there was a research came out last year at Princeton trying to understand the larger scale environmental controls on the TCCs. And they found that a low level vorticity and vertical speed, vertical wind speed is actually 2 very important factors in controlling this TCCs.
Okay, thanks.
Steve, go ahead.
Thanks, Hui. That was interesting. My question is whether this Breyer skill score is computed after de-drifting. It seemed like a lot of your analysis was focused on the increasing climatological bias with lead time, which normally gets removed prior to skill score computation. So can you clarify whether you've done that?
I don't think I've removed anything before the Breyer score calculation, because the calculation is based on the TC occurrence, which is based on the tracked TCs. So I didn't really know how to remove any signal from my tracked TCs. So I would like to discuss more.
Okay, thanks.
Yeah, I think, Steve, so usually we do remove like the lead dependent climatology for like temperature, precipitation and everything else. But yeah, the TC tracks may be more tricky how to do that because it's not like a standard climatological quantity, I guess.
Yeah, so it seems like maybe there is some hidden skill in this system that's kind of being masked by this large bias, that develops with increasing lead time.
You mean the large bias in the mean state?
Yes.
Yeah, so Andrea has a comment in the chat. Would this skill assessment change if looking at, say, ACE instead of tracks counts? And what is ACE, do you know?
Oh yeah, it's the accumulated cyclone energy.
Okay.
Yeah, that's a good question, actually. I didn't look at the spatial distributions of ACE, but in our ENSO analysis, I looked at the interannual variability of the ACE. And curiously, we also found this in the SMILE SMILE forecast, is that the ACE actually has a better correlation with observations in the forecast than the TC count, which is very curious that I don't know why.
And then last question from me. So you alluded that higher resolution may help to improve skill based on prior studies or different models. Do you have any idea by how much, like how much predictability are we losing?
Yeah, thanks to the question. Yeah, it's actually, I think higher resolution would definitely improve because the study by Chia-Ying that published in 2020 and 2018 look at all the TC prediction in the sub-X data set. And in the S2S dataset, sorry, and he found that obviously the European model performs the best, and the models with higher resolution generally has a better performance compared to the lower resolution. So I would say yes, the resolution would improve predictability, but also in the same time, it depends on the model you're using.
Okay, thank you. All right, if there are no more questions, then we'll start moving up into longer time scales, and we'll have a presentation by Andrea Molot from NASA. Go ahead, Andrea.
Hi, so I'm trying to share.
Yep, there's a green button at the bottom of the screen with the up arrow.
Got it. Got it?
Yep, so click the full screen. Yep, the presenter.
Yep, go in there. Okay, this should be it. Okay.
Yep, sounds good.
Okay, so this is a little bit of a sidestep from some of the talks that we've been hearing about so far, looking at CESM results. And I just wanted to talk to this group a little bit about a new so-called weekly coupled reanalysis and forecast suite that's ongoing now at GMAO with the new model. So these are all the people that contributed to the development of this new system. So just in a little bit of a nutshell here, here's a table that talks about what the reanalysis is. Maritime Ocean reanalysis is November 81 to the present. As of now, we've gotten into 1995. The length of forecasts that we're going to be running from it, the retrospective suite, are 9 months, every 5 days with a lag burst. We have a 40-member per month ensemble for the first 3 months. And that's a substantial size running out for 3 whole months. And we are initializing all of this from this Maritime Ocean reanalysis. Our version 2 was released a bunch of years ago. And basically when Maritime Ocean catches up to near real time at the end of this year, the forecasts, the retrospective forecasts are going to catch up, and we're going to flip over to releasing near real-time forecasts from this new system. Here's a little page with some of the characteristics of the system. Anything in purple here is an upgrade from the previous version of the model. So the first upgrade that you'll see is that we're now running a 1/4 degree at the equator, 1/4 degree ocean with 50 vertical levels. And we have this atmosphere ocean interface layer that captures some of the top vertical level is 10 meters. And so this interface layer gets the diurnal cycle parameterized in there because you're not capturing it. The coupled ocean data simulation system, I'll explain in another slide what exactly this is, but the idea is that it's the coupled model running, the atmosphere is being replayed. It's a kind of nudging that we do at GMAO. Precipitation is being corrected over the land. So the land model and actually the interactive aerosol model is seeing observed precip rather than the model generated one. We have a mechanism to correct the water budget to deal with that. And we have an interactive aerosol model here. And so we are also nudging or replaying that to an aerosol assimilated state. So the initial conditions will contain the correct aerosol. And so ocean observations, it's the typical suite of ocean observations that are going into the ocean assimilation. The new thing here is the assimilation of sea surface salinity. And so here's our schematic of what we call our weekly coupled data simulation. This can mean, weekly coupled can mean almost anything. The upshot here is that all of this is done with the coupled model. And so as the coupled model, this is a 5-day segment because our ocean analysis window is 5 days. And so the coupled model proceeds, it's receiving its nudging every 6 hours. Not exactly, it's being done more smoothly than that to the atmosphere as it proceeds. That green line at the top is our predictor segment for the ocean part. As it proceeds with the coupled model integration, it's dropping off states every 6 hours. After 5 days, those ocean states are all collected together. The ocean analysis is performed. We back up 5 days, use the ocean increments. Again, coupled model integration, but now in addition to the atmosphere being replayed in some ways to the OBS, the ocean is also being replayed together. So both of them are marching, kept to the observations together. And the idea is that this continues every 5 days, near real time. What we have now that's nice is because now we've saved these ocean analysis states and we have these atmospheric analysis states, this kind of a system could proceed without running either assimilation and just doing the coupled model and the nudging and use that to set off forecasts. We also have information both from the atmosphere and from the ocean about analysis increments, which tell us about systematic error in the model. So couple of reasons for that motivated us to go to higher resolution, for instance. On the left, for the Gulf and the Kuroshio region, we have what a half-degree ocean model did. That was our version 2 system. In the middle, we have what the quarter-degree ocean model is doing, and on the right are current speed measurements from Oscar. So, we're not capturing all the eddy motions and things like that by any means, but certainly you're seeing variations that look more eddy-like in order to get the surface currents. The other major issue here was the assimilation of sea surface salinity. And basically, given our model, like many other models, rains too much in the tropical Pacific, the water, the ocean is too fresh. And so the SSS data is basically improving it by making it saltier. And that increases the near surface density. Here's a picture of the mixed layer depth, but basically it's deepening the mixed layer depth by putting in this sea surface salinity. What's happening with that is that the deeper mixed layer depth is dampening the Kelvin wave signal and basically helping us not overestimate the El Nino. So this is an example of our default system and the new system with and without the sea surface salinity assimilation and predictions of the very strong El Nino in 2015. This is all from a paper and some work that Eric Hackert did. And now I'd just like to leaf through some of the Meritu Ocean and show you some results from the atmosphere, from the air-sea fluxes, and from the ocean assimilation. On the left, our reference here is the Goddard GSSTF surface flux climatology. And so on the left is Meritu Ocean, on the right, just for reference, is Meritu. And both of these systems are doing a decent job of reproducing fields like the latent heat flux. Here's an example from DJF. Precip, again, the same thing, Meritu Ocean on the left. Here I've got GPCP for reference. These estimates may be a little low, but so far, what we're seeing both in Meritu on the right and in the Meritu Ocean in the coupled system on the left is excessive precip in the tropical IT, in the Pacific ITCZ in particular, Atlantic 2. This led to that freshening that we were seeing. This, again, so Meritu Ocean as of now has reached 1995. We have not yet seen sea surface salinity. I'll talk to you a little bit about the data in a moment. So I'm trying to look at fields that are not actually constrained by the observations. So here we have the Northern Hemisphere sea ice. The extent is constrained to the observations. Those are being assimilated, but the volume and the snow volume on top is not. And so here's a time series of what's happening with the snow volume. Biomass is the reanalysis, the regional ice reanalysis for the Northern Hemisphere. And so it's a decent reference for us. And so we're happy with the way that the track is. It's possible that if you squint, you can see that we're losing a little bit more volume than biomass, but we're also lower in the beginning. So it's not clear, higher in the beginning. So we have to keep track of this. Snow volume, a small decreasing trend, but it's hard to know whether that's correct or not. This picture is a little bit of a reminder of folks what happens when you've got the reanalysis going. So all of a sudden, the altimetry data started to come in, and we made a big difference. There are other impacts on the system that I'll show you, nice impacts. But just a reminder that when we look at trends and when we look at year-to-year changes and stuff, we always have to be careful about this. We're going to hit the Argo period when we reach it, and we're going to also see a big impact of the appearance of all of these Argo data. So again, just for a sense, here from 87 upper right through 93 on the lower left, these are the observations that we have for the near surface temperature, 0 to 30 meters. These are CTD, conductivity, temperature depth, XBTs, the expendable bathythermographs, and the TAU moorings. Again, no Argo yet here. And so here are what the observations look like. And this is the observation minus analysis. And so basically this is telling us what the analysis is doing to the model first guess. And anything blue here means that the model is warmer than the obs, and the obs are trying to cool us down. If we look at the salinity, again, we see, the relative sparsity of salinity data during this early period. And again, these are TAU moorings and the CTDs only. And if you look at the, again, O-A, observation minus analysis, we're seeing the same thing, that the model is fresher than the obs, raining too much in general and over the ocean, and the obs are trying to correct us. And again, the sea surface salinity is going to do a lot more once that data kicks in. Here's a time series of the mean absolute error. This is the observation minus forecast. So this is essentially, this is the field that needs to be corrected by the data. So that's the mean absolute error at the top and the bias at the bottom. And again, once we see the satellite altimetry kick in, this is affecting the background. The model is believing it and using it for its next background. And so we're starting to shrink both the mean absolute error and the bias of the O-F. So that satellite altimetry data is affecting a lot more than just the sea level that we saw. So we like the idea that when we get more data, this stuff is starting to shrink. And so, a quick summary, Maritime Ocean is our weekly coupled atmosphere ocean land reanalysis, 82 to present, public release end of this calendar year. It may leak a little over at the beginning of next year. The ocean resolution helped us a lot, not only with currents, and if you look at the ocean mass transport, the salinity, all kinds of nice improvements that we saw. The bathymetry gets deeper at the higher resolution. And so some of these through flow areas, all of a sudden, water starts to run through there much better. There's no question that the assimilation of the sea surface salinity has improved the tropical density, the mixed layer depth. So we're seeing during strong El Niños, we're seeing a very clear improvement in forecast. The weaker El Niños, we're not seeing that much. And the observations are showing us that near the surface, the model is warmer and fresher, in particular in the upwelling regions. And the impact of the assimilation in general, there are some minor exceptions, is to bring the analysis closer to the observations. So this is mainly to introduce Maritime Ocean and the forecast suite that's ongoing to the community. It could be used for initialization. We're using it now to try to document the advantage of initializing a model with this coupled assimilation as opposed to grabbing separate atmosphere and ocean assimilations. So that was all that I had for today.
Thank you so much, Andrea. So yeah, I really appreciate you talking about your model because we struggle with CSM with all of the choices we have to make, for initial conditions for ocean and atmosphere. So it's really useful to hear your experience in NASA. I think in many ways, the NASA models may be the closest, since you're primarily focused on research. So we're always happy to learn about what you all are doing. All right, and with that, are there any questions? Kathy has a hand up. Go ahead, Kathy.
So I'm just curious, I'm thinking about from the initial condition perspective, I'm guessing since this is new, there's probably not been an attempt to try these initial conditions in a different model. And I was just wondering if by some chance somebody had tried that, or if it would be something you'd be interested in trying to launch forecasts from a different model using these initial conditions.
It's not been tried. This Meritu Ocean is going to get released as a public product through the data center when we're done. Initial conditions, if anybody's looking to use them for another model, we can certainly find a way to get them done. But no, we haven't done that. We do have an in-house version. This system is GEOS coupled to MOM. We do have an in-house GEOS coupled to MIT GCM. And we will be using these initial conditions, interpolating it to the MIT grid and running some decadal scale forecasts with that other model. So we are going to get to something like that, but certainly if anybody else is interested in these, we would be delighted.
Sorry. Yeah, great. Thanks, Andrea. I'm very excited about this this set of initial conditions, and I think there's a nice potential for testing that out in other models.
Yeah, I would second that. So, we're already using the FBIT or the MERA, your atmospheric initial conditions to start WACM, but we have to put in something different for the ocean. So I think that would be really useful for us to try your ocean. And we're also with the Catalyst project, we need to, run some forecasts with the E3SM. And there may be another option for us to try is to use your ocean if we can figure out a way to get that into the model. So we'll be in touch.
Okay, great. Thank you.
Anybody else? And the last question I'll ask, so you talked about largely about the ocean, but not a whole lot about the atmosphere. Do you know already how the new analysis might affect atmospheric skill?
So this is being replayed to Meritu for the reanalysis. When we get to near real time, we're going to end up having to use the new so-called forward processing system. So the replacement for FPIT, Gaga. And we have found, in particular, FPIT is starting to make our forecasts a little crazy. The surface currents in FPIT are getting stronger and stronger with time. And we're getting very cold La Niñas. And we've done some experiments with the newer version of the forward processing that doesn't have that issue of the excessive surface current speeds in the tropics. And things are looking much better. So we are looking forward to doing this. The prognostic fields that we looked at are essentially Meritu. So there wasn't much for us to look at in this reanalysis as compared with Meritu because it looks like it.
Okay. Thank you. All right, last call for questions. Not, we'll move on to Jiao Lo from Ceres and NOAA. Go ahead.
Sure. Can you see my screen well?
Yes, perfect.
Yeah, cool. So hi, everyone. First of all, thank you for giving me this opportunity for presenting today. And thank you all for being here. Today, I'm going to talk about the work I've been doing with Matt Newman and Andy Hui, which is about multi-year scale evolution of ENSO over the past century using model analog technique. In my work, I use model analog technique to make ENSO predictions and understand its predictability. The history of analog technique, especially analog-based forecasting, can date back to 1969, where Lorentz argued that if two atmospheric states resemble each other rather closely, each of the states can be viewed as equivalent to the other state plus reasonably small perturbations. However, due to the short length of record, observations might not be sufficient to find good matches, especially for seasonal to interannual forecasts that we are interested here. So recently, Hui Lee and other people extended the analog concept to the GCM realm by introducing the model analog approach, where instead of using the limited observations as libraries to search for the analog states, the long-term climate simulations are used directly. Basically, model analog is a simple pattern recognition technique. By taking advantage of having large ensemble climate model simulations, we dive into the oceans of climate model data and hunt for the best pattern matches. It's essentially a data mining process, but we can do that quite efficiently. The schematic here shows how the model analog technique works. First, we compare the anomalous states of the observations with the anomalous states of the model simulations to identify the best matches in the models, which is what we call pattern recognition here. So these best matches form our basis of model analog ensembles or initial conditions in the models. The evolution in the selected analog year in the models then defines the basis of a prediction of the target year. Then we compare the model analog-based forecasts with the verifications to get the scale metrics. There are some direct advantage of using model analogs. For example, unlike the traditional numeric forecasting, which initialized using the real-world full-field observations, here we use the model preferred states as initial conditions, and it is unlikely to run into initialization shock like other coupled GCMs have. Also, model analog forecasts are based on the anomaly initialization, so we can efficiently avoid the mean state errors arising from the model structures. And there is no integration needed to analog-based forecasts, which means it's computationally cheap. In addition, as indicated in Ding et al.'s previous paper, forecast errors are more directly related to model errors itself. This slide describes the datasets we are using for model analog forecasts. The verification dataset we are using is from 020C, which is a reanalysis product from ECMWF covering the whole 20th century period. And the library datasets come from the CMIP6 pre-industrial control run. And we make use of 9 CMIP6 models, and their simulation years are longer than 500 years. The advantage that we are using separate training and verification data is that we do not need to worry about the overfitting or underfitting problems like many other statistical tools and machine learning tools. And we don't need to worry about cross-validation since the target state and library state are independent. For the verification dataset, we compute anomalies by removing the 30-year moving climatology to not include the trend component. The figure on the right-hand side shows how the trend has been efficiently removed by using 30-year moving climatology. If we look at the red curve there. For the library datasets, we linearly detrended simulated data to avoid potential climate drift. The region we are interested in is the tropical regions from 30 south to 30 north. In this study, the model analog ensemble size we used is 30. And we use sea surface temperature anomalies only to determine our model analogs. It's worth noting that although we only use the information from sea surface temperature, the analog-based forecasts can be applied to predict the other variables like sea surface height, sea level pressure, and precipitation, as long as we know where the model analogs are located in the models. The maps here show the reconstruction scale, not just for sea surface temperature, but for sea surface height and sea level pressure. By saying reconstruction scale, it basically means how well the model analogs we selected can represent the observations. Generally speaking, the model analogs we selected will represent the features showing the observations, especially in the tropic Pacific, with correlations over 0.9 in the equatorial Pacific. However, the ENSO westward extension is apparent in the semi-Pacific models as shown in the black circles, which needs to be properly addressed in the future model development. In order to know how good our model analog forecasts are compared with the state-of-the-art GCMs, here I compared our model analog forecasts shown on the top with the hindcasts generated by the ECMWF's operational seasonal forecasting system, CS5, shown in the bottom layer. It's worth noting that it is an apples to apples comparison. Here we use the same verification dataset and initialized in the same month, covering the same period. The plots here show the scale evolution of Ninus 3.4 over the 30-year moving hindcast window as a function of least seasons initialized in May on the left-hand side and November on the right. First of all, I like to mention that because of computational cost, the GCMs tend to initialize in certain months, like May or November as shown here, but it's actually the strength of model analog forecasts, which can be initialized in every single month and can give you the forecasts in like 15 minutes. It's computationally cheap. And put that aside, if we have a look at the scale itself, actually the scales are comparable. Because of using different color schemes here, I need to point out our light yellowish color is equivalent to their brownish or orangish color there. So now we can see that to some extent, the model analog forecast is doing better for example, predicting the second year ENSO events in the recent decades. After doing the comparison, I'm confident to say that our model analog forecasts are competitive or at least comparable to those generated from the state-of-the-art GCMs. The figure here shows the Ninus 3.4 scale evolution, where I divided the whole period into the same 30-year moving hindcast windows and computed the AC scale in each chunk of period. On the y-axis is the forecast lead times ranging from 1 month up to 2 years ahead. On the x-axis shows the calendar year, and the AC scale have been centered in each 30-year period. We can definitely see that ENSO scale is climbing up in the recent decades. It leads to a very interesting question if there is some changes of ENSO predictability, which is still my ongoing work. In order to figure out what caused the increased scale in the recent decades, as we saw in the previous slide, here we examined the signal-to-noise ratio, which seems to be a direct metric to understand the relative importance of signal and noise processes in ENSO predictions. For example, we might expect that the increased scale is either because of more predictable signal we have in that period or less noise. So here I show the model spread, signal component, and the resulting signal-to-noise ratio of Ninus 3.4 predictions as a function of forecast lead times. We can see that the model spread on the top has strong seasonality, but in general, the error grows quickly after the first few months, while the signal component, which is defined as the absolute value of ensemble mean anomaly, acts as a nonlinear filter. It removes most of the noise and only keeps the predictable signal component, which corresponds well with the ENSO events. The resulting signal-to-noise ratio shown on the bottom resembles the features shown in the signal component. So from the perspective of signal-to-noise ratio, the results suggest that signal component tends to dominate ENSO scale evolution, while the noise component, the error growth is inevitable but less important compared with the signal component. As we all know, compared with deterministic forecasts, probabilistic predictions are of particular value for decision makers to take preparatory actions when the forecasts reach certain threshold. However, as some studies suggested, the success of the deterministic matrix cannot guarantee the success of probabilistic matrix. So here I show the ROC scale of minus 3.4 predictions at different lead times for the La Nina condition and El Nino condition. And the values in the brackets indicate the ROC area underneath each ROC scale curve. The reason I'm interested in ROC scale here is because it is a good metric to measure if the forecast system can clearly distinguish situations leading to the occurrence of an event of interest, which is a hit rate on the y-axis here, from those leading to non-occurrence of the event, which is a false alarm rate on the x-axis. The perfect ROC scale would line up with the y-axis, which means there is no false alarm, and the perfect ROC area should be equal to 1. We can see that these models are doing reasonably well in terms of hitting the El Nino and La Nina events, and also those models are doing slightly better in predicting El Nino than La Nina if we look at the values in brackets. However, the better scale of El Nino condition shown here largely depends on the time periods we are interested in, and also depends on the selections of the models and ensemble members and thresholds as well. So the sensitivity of probabilistic forecast to these factors needs further investigation. To test if the predictive scale trend we saw in the previous slides is robust, here we examined the scale evolutions over 7 SST datasets. Essentially, we use 7 different SST datasets as verifications to do some independent ENSO predictions. And the figure here shows the predictive scale evolution of minus 3.4 over the 30-year hindcast windows. The takeaway message here is that no matter which verification datasets we are using, the scale trend is robust and significant, especially for the longer time leads, for example, scales at 12 months lead. We do see the elevated scale in the recent decades through all the verifications as well. This slide shows the same scale evolution, but for the independent mean sea level pressure datasets. It is worth noting that mean sea level pressure didn't participate in selecting the model analogs. All the model analogs are determined from sea surface temperature only. That is why we call mean sea level pressure as independent variable or dataset here. We are taking advantage of model analog ability to forecast any model variables, not just those used to choose analogs. Again, we see that the results are not sensitive to the datasets used to choose analogs. And we can see the same elevated scale for the equatorial southern oscillation index in the recent decade as well. To sum up, our model analog-based forecasts are comparable to the operational GCMs. ENSO scale underwent pronounced long-term variations. The second-year ENSO scale in the recent decades has been improved in different verification datasets, and the ENSO scale trend is robust and significant no matter which verifications were used. And signal component dominates the ENSO scale evolution, which tends to be associated with strong ENSO events, while error growth is quick and inevitable, but less important compared with signal component. So right now I'm working on finding the reasons why we saw such elevated scale in the recent decades, which is still my ongoing work. And I guess I'm going to stop here, and thanks for listening.
Thank you very much. Are there any questions? Jerry, go ahead.
Yeah, that's very interesting. And it's, as I understand it, you're using tropical SSTs 30 north to 30 south, right?
Yes, I am.
So it's intriguing that you could actually look at processes in ways that you could actually increase the domain of SSTs, or just take SSTs over one basin and then try to see if you know, if you get hotspots and that could relate to some of the machine learning methodologies that are being used. But I think there's other things you could do with this method once you've got it going, right? Have you thought about doing that?
Yeah, definitely we can extend the region, not just focused on the tropical region, but for the ex-tropical region as well. I guess Hui and other people has already done that in their 2018 paper. So right now, my basic focus is UNSO region and the predictability of UNSO. So definitely that's one possibility, yeah.
Okay, thanks.
Great, thank you. There's another question from Zhengjun.
Look like the scale for warm phase is larger than for a cold phase. So why is that?
So yeah, like I said, because now I focused on the entire period, the 20th century. But if I look at the sub-period or the, for example, I mean, the result is sensitive to the choice of ensemble members and the time periods we are interested in. So it's not like permanent or stay there forever. So, but just for now, we saw that the El Nino condition is slightly better than La Nina condition.
One my speculation is probably that the associated with the symmetry of the intensity of the warm and cold phase. Statistically, the warm phase a little bit stronger than the cold phase. I think probably that is the case.
Yeah, you might be right. Yeah, in terms of the variance. Yeah.
All right, any other questions? Steve.
Yeah, I'm just curious how well the model analog technique does in terms of ENSO magnitude.
Yeah, that's a great question, and we are still looking at it. But for the longer lead, the amplitude kind of decays. It's inevitable, but I haven't looked at the actual like how much it decays that in terms of amplitude. Yeah, but I will definitely look at that.
And then lastly, have you looked at the recent years, so the recent La Nina?
Because okay, yeah, I guess this figure can explain something. Yeah, I mean, some data sets extend to 2020, and but I haven't specifically looked at the recent of the 21st century. So.
Okay, thank you. All right, I think if there are no more questions, then we'll move on to the next talk by Samuel Mogan. And Zhengjun, you still have your hand up. I'm assuming that's from before, but if you put it down, then I'll know for next time if you ask any question. Thank you. So Samuel, go ahead.
Which screen is shared right now? Is it the presentation?
Your big screen, a good one, so it's perfect.
Awesome. I'm never sure about that. Thank you. Good morning, everyone. My name is Sam Mogan. I'm a PhD student at the University of Colorado Boulder, working with Nikki Lewandowski. Today, I'm going to be talking about some ongoing work looking at multi-month predictions of ocean acidification signals in the novel CESM SMILE. This is ongoing work with Nikki and Steve Yeager. Just as a little background review, climate change is having a lot of effects on the ocean. So we're seeing a dramatic rise in temperatures, a decline in the pH, which is an increase in the acidification, and a decline in the total oxygen content. So there's a lot of uncertainty on near terms about what these are doing and how these are changing. And today we're going to focus specifically on changes in ocean acidification in the near term future. So ocean acidification matters a lot. It has direct effects on shell forming organisms, making it harder for them to form these shells and easier for their shells to dissolve. This can have upstream effects on food webs and eventually disrupt ecosystem and ecosystem services. So it's very important, and it would be really useful to understand the evolution of ocean acidification on the near term. Previous work has explored the ability of near-term initialized models to predict features of the ocean carbon cycle, but this work is limited by relative scarcity of observational data. Lewandowski et al. Showed that a similar modeling framework, the CSM DPLE, had a high predictability for near-term ocean carbon uptake, But this is directly comparing the initialized model with model reconstructions rather than observations due to a scarcity of observational data. Brady et al. Also took a look and looked at the predictive skill of ocean acidification in the California current system, comparing the CSM DPLE to observations, and found really high skill multiple years in advance, allowing skillful predictions and a skillful estimate of what ocean acidification would look like in the future. So there's a lot of potential for trying to understand ocean acidification in the near term, but this is been really affected by a lack of observational data. So in this study, we're using the novel CSM Smile to predict and the skill of ocean acidification on monthly timescales and try and understand evolution. To go about doing that, we rely on 3 primary data sets. First, and most importantly, is a recently developed gridded observational product, Ocean Soda ETHZ, which is a unique and relatively novel tool for studying ocean acidification. So while most gridded observational data products in ocean BGC are relatively short timescales, we have relatively long data from 1985 to present in this gridded observational reanalysis. And this allows us a longer window in which to assess model skill of model output. So this is very exciting and has a lot of potential for future work. We also took a look at the CSM2 large ensemble as an uninitialized comparison for the initialized data set. And then finally, we have the novel CSM Smile. Smile is basically built off of a model reconstruction, which is initialized 4 times a year. So we have a model reconstruction, which is basically a best guess at the real world ocean sea ice evolution, which is then initialized multiple times a year and integrated for 2 years for each initialization. Just in comparison to the previous generation CSM DPLE, CSM Smile is run in CSM2 from 1970 to 2019 with 4 annual initializations capturing seasonal spread. Integration is a lot shorter than CSM DPLE, but we can look at shorter timescales and influence of seasonal initialization with fewer ensemble members. There's a lot of questions about what CSM Smile is able to accurately predict. How are we actually going to go about studying our ocean acidification signals? The way we approached this was basically taking the seasonal climatologies from our model reconstruction and from our observations and just correlating these anomalies and seeing which values lined up the best and which the model reconstruction is most accurately reconstructing. And we found that omega aragonite had the highest correlation between model and observation. So we moved forward and we wanted to focus on omega aragonite as a signal of ocean acidification. Omega aragonite is basically the aragonite saturation state, and it is the dissolved carbonate over the carbonate value at saturation. So we need values well over 1 for shells to be formed. So we need a really super saturated omega aragonite level. When values fall too low, shells begin to degrade. As you can see on the image on the right, these are shells subject to different levels of ocean acidification, and eventually they degrade and eventually dissolve. So when processing our initialized model data, we first removed climatological drift from all of our data products and long-term trends, the long-term ocean acidification trends. And then after removing these signals in all our data sets, we compared data at different lead times from model initialization. So in this slide, we've selected the first lead time for our initialized models for a February initialization. And we calculated the anomaly correlation coefficient between our initialized model forecast and our observations in the top panel, found a very high correlation here. We also took a look at persistence forecasts. So basically taking the observations from the month previous to initialization and auto-correlating them out into the future to see how well the observations predict themselves. And then finally, we just took the uninitialized forecast and matched it with the observations at the same time scales as the initialized forecast and calculated a correlation value. And here we're using anomaly correlation coefficient as our measure of skill. So at least in this admittedly cherry-picked section, we find that the initialized model is most correlated with the observations and does a really good job at reconstructing the observational signal. But how does this actually look on a global scale? So this is showing for each of the 4 annual initializations, February, May, August, and November, the first 3 lead times. So after initialization, the first 3 lead months, the skill globally for omega aragonite from the initialized model as compared to our observations here. Red values here are very good and indicate a very high correlation. And we find that these early initializations show very high anomaly correlation coefficient values up to 0.9 to 1 in certain regions. These values begin to drop around the third lead time, but remain really high, especially in specific regions like the Eastern Pacific and the North Atlantic. Zooming out a little bit, this is just the global skill for the whole first year. So I've already showed you the first 3 lead times, so the top 3 rows here. And now we can just look at and see how the skill declines over time. Different initializations have different drops in skill. So you see the February and May initializations remain relatively high, at least in the Eastern Pacific and North Atlantic for the majority, at least the first year. I'm only showing the first year rather than the 2 years of initialization, just to keep it a little tighter. So some regions are still have really high skill, especially for these early year initializations, but overall skill is dropping over time. I also took this initialized skill and compared it to skill over a persistence forecast and just took the difference. So skill minus the persistence forecast skill. So these plots are just showing the gain in skill from initialization. Red values here indicate that there was a gain in the skill from initialization relative to our observations persistence forecast. And we find that our initialized forecast is doing a much, much better job than persistence. Values remain very, very red and very high gain until the end of the first year of initialization. So it's working very well, especially compared to persistence. We also did the same thing comparing the skill of our initialized forecast to an uninitialized forecast over the first lead year. We find in the top there is a lot of gain over the uninitialized model version from our initialized forecast, so the values are quite red. By the end of the first lead year, the difference has declined a lot, although generally globally, we're still seeing a decent gain in skill over our uninitialized forecast. I also took a look at the global average skill and did an analysis there. So this is showing for each initialization, February through November, the skill, which is our solid line here globally, starting off very high and declining by the end of the model integration. We also took a look at the uninitialized forecast skill relative to our observations and our persistence forecast, which is the dashed line at the bottom. We find here that initialization has a lot more skill than other forecasts for more than a year, around 12 months, the 12-month lead time, the uninitialized forecast seems to approach the skill of the initialized forecast, but it is relatively higher. So I showed you earlier that a few regions had a much higher skill overall than the global average. So we wanted to just zoom in on a few of these regions. So we selected some specific areas. So we took a look at the Nino 3.4 region. Previous analysis in SMILE has been done in the Nino 3.4 region. We wanted to just compare this high skill. We also looked at the California current system, which is a very, very productive marine ecosystem, and the region of previous acidification study by Brady et al. That I showed you earlier. And then we also focused on the North Atlantic and just wanted to see how well we could predict carbon in the North Atlantic. So here, again, are just a time series analysis for this predictive skill in each of these regions. Starting on the left in the California current system, we see a very high anomaly correlation coefficient for the first year. And these values are basically, there's a gain in skill over both our uninitialized and our persistence forecast over this time period. This is very interesting as California current system is the subject of a lot of study and could potentially be very useful in understanding short-term predictions of ocean acidification. We also took a look at the Nino 3.4 region and found very high skill, which was much better than an uninitialized and persistence forecast out to about a year. And then finally, in the North Atlantic, we found our persistence forecast did very poorly there, but our uninitialized did only slightly worse than our initialized forecast. In conclusion, the CSM SMILE has very high skill, especially at early lead times for ocean acidification predictions. CS SMILE has a higher skill than persistence and uninitialized forecast out to more than a year. And then regional potential, there's regional potential for skillful forecasts up to 15 to 18 months in advance. As I mentioned, this is part of ongoing work. And in the future, we plan to explore the dynamics of driving the differences in seasonal forecasts and why they might fare differently over time. And also just explore the drivers of this predictive skill generally. We also want to look at the predictability of extreme states in these data products, and then also eventually move and look at the predictability and predictive skill of other ecosystem stressors and functions, including productivity and oxygen, although this is kind of an issue with relative scarcity of observational data. And I am ready for any questions now. Thank you.
Great, thank you so much. There's a clarification question in the chat, or maybe you can just answer it out loud. Could you please once more define what an initialized forecast is, please?
Yeah, so let me go back to another slide. So basically you have the model reconstruction. This is the forced ocean, CSM forced ocean reconstruction, basically a best guess at the real world ocean. And then at certain times, which are described later, so February 1st, May 1st, August 1st, and November 1st, you basically stop the reconstruction from, the uninitialized forecast. I saw it in chat. Yes, so we just looked at the CSM2 large ensemble. So this is a 50 ensemble. I just took the average of the 50 ensemble members of CSM2, rather than being forced over time with real world atmosphere and terrestrial forcings of the ocean. This is just CSM's evolution of the ocean that would be used to predict out to 2100, basically, with different forcings. So it captures a lot of the dynamics, but it's not as in touch with the real world as the initialized forecast, which is based on this model reconstruction.
Thank you, Judith. Does that answer your question?
Yes, thanks so much.
All right, then we'll move on to Steve.
Yeah, Sam, I was just curious if you had any thoughts on why your persistent skill shows some dramatic increases at long lead time.
Yeah, that's something we've been talking about, and we really don't have a great idea. I think especially interesting in the California current system, sort of at the end of initial integration, we see the persistence forecast is almost better. I am curious if this has to do with the development of sort of climate modes or some sort of teleconnective pattern over this time period, but I haven't had a lot of time to think about this directly yet.
Any other questions? All right, well, thank you very much. And we'll come back to the SMILE forecast in the afternoon and including an analysis registry, just so everybody's keeping track of what everybody else is doing. All right, for our last morning talk, we'll hear from Jean Vu.
Can you see my slides well?
Yep.
Thank you. My name is Xian Wu, and I'm a postdoc working at NCAR. I'll be talking about the effect of volcanic eruptions on multi-year to decadal predictions in the tropical Pacific Ocean. This work has been in collaborations with my advisors, Steve Yeager and Clara Deser, and also Nan Rosenblum at NCAR. Strong volcanic eruptions can affect global climate on seasonal to multi-decadal timescales. For example, the aerosol particles released from volcanic eruptions can reduce the incoming solar radiation at the surface and cools the global mean surface temperature. And they can also project onto climate modes like ENSO et al. And this volcanic forcing is expected to provide an important source of climate predictability and has been included in the CIMIC 5 and 6 decadal prediction systems. A study by Jerry Neal et al., they find that the CIMIC 5 models show a decrease of prediction skill in predicting Pacific SSTs. near the strong eruption of Pinatubo in 1991, they hypothesized that the correlation scale, pattern correlation scale is degraded by the Pinatubo because in observations, the Pacific SSTs are largely driven by internal variability, while the multimodal mean hindcasts average out internal variability and represents a forced response to volcanic forcing. To more comprehensively investigate and verify the influence of volcanic forcing on multi-year to decadal predictions, we make use of two suites of forecasts conducted with CESM Huang. The first is the DPLE, and a parallel set of DPLE excluding the historical volcanic forcing. The volcanic aerosol forcing used in DPLE is majorly contributed by the 3 tropical volcanic eruptions and 2 small ones in 1970s. DPLE consists of 40-member ensemble forecasts initialized in November 1st of each year during 1954 to 2015 and run forward for 10 years. These forecasts are initialized from the same observed oceanic and sea ice states, but with slightly different atmospheric initial conditions for each initialization year. They are also conducted under the CIMIC 5 external forcing. DPLE NOVOC has the same setup except for the volcanic forcing and also a smaller ensemble size of 10. We will consider the different ensemble sizes and use bootstrap methods to test the significance when we compare these two forecast sets. First, I'm showing you the correlation scale for annual mean sea surface temperature anomalies and land surface air temperature anomalies in DPLE and DPLE NOVOC for 3 selected lead times from lead year 1 to 5, 6 to 10, and 1 to 10. In both DPLE and DPLE NOVOC, the correlation scale is very high almost everywhere. This is because the model is able to predict the anthropogenic warming trend of the surface temperature. The differences between DPLE and DPLE NOVOC shows that including the volcanic forcing in prediction system degrades the slightly but significantly degrades the correlation scale over the tropical, Central Eastern Tropical Pacific. In these slides, before calculating the correlation scales, we quadratically detrended both observations and forecasts to exclude the high scale arises from the anthropogenic trend, warming trend, and to focus on the variability on multi-year to decadal timescales. You can see that the correlation scales decreases almost everywhere compared to the previous slides. And the differences between DPLE and DPLE NOVOC become more pronounced, especially for the tropical Pacific. Besides the tropical Pacific, we also identify significant differences in other regions, for example, Asia area, South America, and tropical Africa, which requires further examination. But the rest of my talk will be focusing on the tropical Pacific Ocean. To test if this scale degradation by volcanic forcing is robust across different lead times, I'm showing you the correlation scale of the Central Eastern Tropical Pacific SST anomalies as a function of lead times with time intervals of 1-year average to 10-year average. For both non-detrended and quadratically detrended results, we find that the DPLE shows lower correlation scale than DPLE NOVOC for almost all of the lead times. That's confirming the robustness of skill degradation across lead times. Also, for a specific time window, we can see the degradation is more severe at longer lead times. For example, comparing this lead year 1 to 4 to lead year 7 to 10. Then we wanted to find out what causes the prediction scale differences between DPRE and DPRE NOVOC. I'm showing you the time series of Central Eastern Tropical Pacific SSTs in observation, DPRE, DPRE NOVOC, and also the uninitialized simulations, large ensemble as a reference forecasts, reference predictions. And note that here I'm showing you the raw values of SSTs without any drift correction or detrending. So we can see that the significant differences between DPRE and DPRE NOVOC are denoted by the gray shading, and they tend to occur around the forecasts initialized around the major volcanic eruptions. And DPRE shows cooler multi-year and decadal SSTs around the major volcanic eruptions compared to the DPRE NOVOC. And this direct cooling effect of volcanic forcing on these particular years can also cause the long-term drifting climatology in DPRE than DPRE NOVOC. And this is valid for all lead years from 1 to 10 years. So due to these different climatologies, the dedrifted anomalies shows differences in period that there is no volcanic forcing differences or very weak volcanic forcing differences. And during this 1970, around 1970 and after 2000, DPRE shows a warmer signal than DPRE NOVOC. Also, this drift correction process weakened the differences around the major volcanic eruptions. For example, for the lead year 1 to 10, the original small magnitude of cooling effect becomes insignificant after the drift correction. Then we further quadratically detrend this time series. The differences around the major volcanic eruption remain robust, but the differences after 2000 disappear. These results suggest that the volcanic eruptions can not only affect the years around their occurrence, but also can affect the long-term climatology and trend in the decadal prediction systems. Next, we will zoom into the years for the 3 major volcanic eruptions. I'm showing you the 5-year average sea surface temperature and land surface air temperature anomalies after 3 major volcanic eruptions. In observations, for all the 3 cases, the central or eastern tropical Pacific shows SST warming. This SST warming is not captured by the DPRE forecasts, but to some extent captured by the DPRE NOVOC. The difference map between DPRE and DPRE NOVOC shows that the volcanic forcing causes global cooling, including the 5-year cooling over the tropical Pacific. To further understand what are the processes by which the volcanic forcing causes this multi-year SST cooling in tropical Pacific, I will zoom into the monthly evolutions of tropical Pacific SST anomalies. I'm showing you the monthly time series of Central Eastern Tropical Pacific SST anomalies around the Pinatubo eruption. The observations is shown in the black curve. The tropical Pacific SSTs is highly correlated with the Minu 3.4 index and thus related to the ENSO variability. And the colored curves represent the ensemble mean differences between DPLE and DPLE NOVOC initialized at different start dates as early as in the one initialized in November of 1995, about 5 years before the volcanic eruption. For the forecasts differences at different lead times, they all tend to show 3 stages of SST changes. First, this initial SST cooling tendency, then an SST warming tendency, and followed by an 1 to 2 year long SST cooling tendency. And this last phase of SST cooling is responsible for the formation of 5-year average cooling. And to further understand what processes cause these different SST changes, we make use of the ocean mixed layer heat budget analysis. We find for DPLE, DPLE NOVOC and their difference, we find that the initial SST cooling tendency is largely driven by shortwave reduction. And the second phase, SST warming tendency, is dynamically driven related to the El Nino development, but also damped by the shortwave reduction and long-wave reduction. The third phase of SST cooling tendency is also dynamically driven related to the La Nina response. In summary, we find that the volcanic forcing significantly degrades the skills of CESM in predicting multi-year to decadal SST variabilities in the Central Eastern Tropical Pacific. CESM tends to produce multi-year to decadal surface cooling in the Tropical Pacific in response to volcanic forcing due to both shortwave flux reduction and ENSO dynamics. While in observations, the 3 major volcanic eruptions coincided with above normal SSTs in the Tropical Pacific in association with El Nino events. The model observation discrepancy around the volcanic eruptions could be due to the model errors in simulating Tropical Pacific response to volcanic eruptions or the too strong internal variability in observations. Thank you. I stop here and take any questions.
Thank you so much, Jen. That's super interesting. Are there any questions? Jerry, go ahead.
Hi, John. Thanks for that. I was just, and you explained this, and it kind of went by quickly, but you were doing 2 different kind of adjustment operations. You were doing a detrending, and then you're doing a de-drifting. And I think I understand the detrending because you're removing the long-term warming trend from increasing greenhouse gases. But I was wondering if you could say a little more about how you do the de-drifting.
The drifting process is just to remove the time-dependent climatology to get the forecast anomalies.
So you're removing this reaction you were talking about, the cooling, the warming, and then the cooling. Is that the de-drifting?
I'm just removing the climatology across this about 60 years as a function of lead years in both DPLE and DPLE.
Oh, okay. So that's kind of like a drift correction.
Traditional way of drift correction. But here I wanted to highlight that the drifting climatology is different between DPLE and DPLE NOVOC.
Right.
Which is cooler in DPLE due to the volcanic eruptions.
Oh, okay, thanks.
So yeah, following from that, if you already removed the cooler signal, then isn't it a little odd to compare them, right? When you look at the individual events. Because yeah, in one, I guess, yeah, it makes it problematic that the climatology is not the same. Because to really get then temperature signal, it would be a little different if you remove something more similar, right? So I wonder if the methodology partly impacts the results, but I don't really have a solution, but.
Yeah, we think about that. We still think we should remove the different climatologies because we have a new mean state due to the volcanic forcing, and then we are trying to look into the anomalies based on the new mean state.
Okay, so we got a few more hands up. Let's start with Hu.
Hi, thanks for the interesting talk. So you show that there are kind of three stages. Three stages of bias after the eruption. So I wonder, have you looked at the free-running CESM simulation, whether you can see the same from the free-running CSM simulation?
I actually looked into that, but I didn't include that here. The CESM1 large ensemble is within the spread of the forecasts at different lead times. It's also showing the similar tendency, like cooling followed by warming and then longer time cooling.
Okay, yeah. So it's not related to initialization. So it's kind of more intrinsic thing.
Yeah, but the magnitude of the tendencies here might be related to the initialization.
Okay, yeah, thank you.
Ayumi, go ahead.
A very interesting talk. So do you have any thought on why the CSM1 does not simulate the ENSO response after the volcanic eruptions?
There is an El Nino response, but it's weakened by the shortwave reduction.
But if you compare the left-hand side, this SST, the curve, it seems that it does not simulate the El Nino cases after eruptions. So I'm wondering have you checked the westerly wind burst or anything that is known to trigger the ENSO after the volcanic eruption? I'm just wondering what is missing in the models that does not capture this ENSO signal. If I understand correctly.
Yeah, it's hard to say if it's model errors or just that the observations is largely driven by internal variability. It just happened to be El Nino, a series of El Nino events for this case. And we only have 3 cases during this period. So it's very hard to say if model is doing wrong or the observations is driven by internal variability.
Thank you.
There's a question from Andrea in the chat. Do you know how the stratospheric aerosol optical properties are treated in their runs with explosive volcanoes? We found this to be important for Pinatubo.
I'm not quite familiar with that, but it uses the volcanic forcing fire for the CCSM4 development, I think, and it has the spatial variance with latitudes and only several layers for the vertical injection. I'm not quite familiar with this chemistry part.
There is a hand up from Jerry. So is there another question or can you help answer that question?
Yeah, well, just a little follow-up. So in looking at the slide you had before this one, where you're showing the time scales, the response, it looks like the initial cooling is about 6 months if Pinatubo went off in June. And then it's like a year of warming and then a couple years of cooling, right?
Yes.
And then that's where you're saying it doesn't, that evolution doesn't match up with what happened in the observations, which is why there's less predictive skill. But what about, I assume that same response occurs for every volcanic eruption in the CSM, right?
Yes. But the response is more significant for the Pinatubo one than the other two.
Right. Okay, thanks.
Thank you.
And I think to get back to Andrea's question, I think these are, you just prescribing aerosol optical depth in the files, right? Steve, do you know how these volcanoes are prescribed in these initialized runs?
No, we'd have to ask Nan. She's not on.
We made some runs with Pinatubo, and we treated those aerosol the way we would treat aerosols that appear in the troposphere. And the chemists have a better way of doing this. And so we changed the way that those things are treated, the optical depths, essentially, the sizes. And it had a big difference in terms of how the model responded to Pinatubo. So that's why I was asking. Thank you.
Thank you.
Yeah, I think we would need to verify with Nan, because in Wacom, the aerosols, they're actually you inject the SO2, etc. And I think we might be making then the AOD files from that. Or either that or we take them just from some other database. So we can clarify with Nan. Steve, did you have another question?
Yeah, I just wanted to follow up on the plot that Jan was just showing. It seems like this excessive cooling in DPLE is really only occurring for these hindcasts that were initialized quite a bit before Pinatubo, right? And so it suggests that there might be some kind of interaction between the forcing and the development of model bias, that's explaining that cooling that you don't see in the hindcasts that are initialized, just prior to the volcanic eruption. Is that how you're interpreting that plot, Jan?
Yes, I think the forecasts like initialized right before the volcanic eruption, they have more memories from the initialization and more closer to the observations compared to the forecasts initialized at earlier dates. So I don't know if that will help to cause a weaker response for the forecasts with later start dates.
Thanks.
All right, thank you. All right, well, thank you again to all the speakers from this morning. We're almost to the top of the hour. Elizabeth has posted the link for the CGD seminar in the chat if you'd like to watch. And then we'll have a short break and be back here at 12:30 for some talks on decadal prediction. Thank you, everyone.